questions.
Be curious.
Those who can imagine anything can create the impossible.
Good afternoon. My name is Ceely. I'm the Director of Technology Strategy at Digital Catapult, and I'm delighted to be here to chair a session, to moderate a session on when will quantum computing have its ChatGPT moment. And it's a fascinating time. So it's 125 years since the science of quantum was first emerging. And it's 100 years since quantum mechanics was defined, which is why this year is the year of quantum, according to UNESCO. And it's roughly, I think it's roughly 40 years since the idea of a quantum computer was first imagined, and the first algorithms were kind of discussed. And now I'd say probably in the past 10 or 20 years, we've shifted a little bit away from thinking about quantum as a scientific thing to quantum computing as a science and engineering activity. Huge amount of engineering, looking at engineering of very small things, looking at cooling, all of the systems that you deal with that, looking at how you deal with photons, for example. Photonics is a really critical part, and all of the engineering to engineer quantum computers. And we're getting closer. I'd say we're getting closer to what a usable and useful quantum computers might be. And the question is, when will it move from the science and engineering lab and starts to be something that people can actually use, normal people? When will it have its ChatGPT moment? And so I am delighted to have three excellent people to come here and discuss this with me. And first of all, I would like to ask Gabriella, who is the Managing Director of Research and Network Strategy at BT, to come up onto the stage. Thank you very much. And then also, I would ask Ceely, Chief Science Officer of Horizon Quantum, to come and also join me on the stage. And Laurie Thorpe, Strategy Advisor at IBM. And could you... And I will join them down there. So, what I would like you to do, first of all, so I've got a very retro handwritten notes here. What I would like you to do, first of all, is if you could introduce your perspective on this, what excites you about quantum computing? Introduce obviously yourself and your company, but just what excites you? What are the use cases? What is the potential that is really interesting for you? If I could start with you.
So I would like to start saying why BT and why quantum, and that we've been doing research in quantum for many years. Why? Because of course we follow the potential of the quantum computer. We'll talk about that. Super exciting once it will be there, but also because we understand that there will be so much power that not only will it bring a lot of opportunities for our customers, and we always say what matters for our customers matters to us, but it will also be a tremendous threat for security. So as the national champion of connecting our customers and being that most trusted connector of the UK, our big interest is to understand the so what of quantum, not only for our business. We look, of course, at quantum for networks. What will quantum do for network planning, optimization, etc. at some point. But we look at also the networks for quantum. So I mean, how do we build the networks of the future to to serve the opportunities of the quantum computer, but also to mitigate for the threats. So we've been focusing a lot on quantum secure comms, and we also have been focusing a lot on quantum sensing. And we were the first in the world to launch a quantum key distribution trial in London in 2022. with first customers were HSBC and EY, and we're expanding that. And the purpose of doing that was exactly to kind of understand what are those use cases in terms of opportunities and threats. But so that's a little bit of the story why BT and why we care so much, because it will matter a lot to our customers.
Yeah. Great. We'll get onto that a bit later on what will matter and when. But next, Ceely, if you could.
Yeah, so I started out as, on the other side. I did my PhD in quantum computing, and this was way before, it was ever interesting to industry. I think there were some, interest in NEC back in New Jersey. I was in MIT at the time. And at the time we know in principle how to, speed up certain problems, certain classes of very difficult problems that are intractable for today's computer. And but the problem is, it's hard to get to useful quantum computing in the sense of coming up with the implementation, the programming languages and things like that, or to write the programs and to execute it on quantum computers, and to also build the quantum computers themselves, because they were not large enough and reliable enough to run the programs that could be useful for us. So I think. But that said, we are at an inflection point, and that's what's so exciting. I think the first few cases that would come up probably would be some of these, applications that we know of that are computationally intensive. But I think what excites me the most is that there are a lot of the space of complex problems is very large, and I think there are a lot of untapped potential there for this technology to be disruptive. And this is what drove me to join industry from academia. So at Horizon Quantum, which was started by my postdoc advisor, Dr. Joe Fitzsimons, and myself, and a PhD student from his group, we left academia to start Horizon Quantum. And we are a quantum software company headquartered in Singapore. And we are looking at building software infrastructure. So everything from compilers, programming languages, that support abstraction, like loops and things, and for loops, increment loops, subroutines, things that you take for granted these days, and maybe too much, because I think when I talk to students in college, they're like, "What? Is this not Python?" Right? But things that you take for granted now that we need to build for quantum computers.
Great. We'll touch on that a little bit later. And Laurie, if you can introduce yourself and what excites you about this.
Sure. So Laurie Thorpe, I'm part of IBM Research, although my background is in telecommunications. So a couple of things that really excite me. So IBM has been obviously very active in building quantum compute capabilities. It is one of the key investment areas, and we are arguably world leader in quantum computing. A couple of things that really excite me. So I am old enough to remember sort of computers becoming more accessible the first time round. I remember the excitement when at the time I was in elementary school. We bought a computer. It was 4K, and we were over the moon because we had access to this machine, and it was all amazing. Quantum computing is effectively a once-in-a-generation. It's an inflection point where we're getting these new capabilities that will really open doors to huge amount of potential. And I think we've really only just scratched the surface of what that potential can actually achieve. I agree, we are at an inflection point. So we're now seeing, after all of the work that's gone into getting us where we are today, we're now sort of starting to see what that means and how that can actually be applied. So I think it's a really exciting time for quantum computing, really exciting that we have access to this completely new revolutionary capability, and excited to see what we're actually going to do with it.
Thanks. I was going to pick up on that point, because when you say we're at an inflection point, I've been reading. You read in the press, and there's a CPU that's announced, or QPU that's announced every month now, which makes a big step forward. So I was wondering if you could tell us give us a sort of, Laura, if you could give us a quick overview of where you think we are on the maturity of quantum computers in terms of what they can achieve. And there's this sense that it's still some time out before we can get a truly powerful quantum computer. And what your sense of what that timeline looks like?
So my sense is, we need to think about, now we've moved away from effectively theoretical physics, and we've moved to a space where we've actually got capabilities. These capabilities are going to evolve, and they will evolve in gradual steps across different dimensions. So there is the evolution of the scale of the quantum computer. So often what we're seeing is a new chipset that has X number of qubits, and then the next one that has 2 times that number of qubits, and all of these things. We're also seeing announcements like the one made by IBM last year, which was around error correction. And I guess maybe Paul will get back to that a little bit later around why that's so critical and so important in terms of making the quantum computers more useful, and building out the capabilities that are actually going to help us solve real life problems. So I think where we are at the moment, IBM defines this the era of quantum utility, progressing towards quantum advantage. So we're at a point where quantum computers are starting to show useful capabilities that go beyond what we can do today with classical computing. But it's not going to be sort of one day we wake up and it's there. It will continue to sort of move in steps and continue to evolve.
Yeah, I get the impression there's a lot of rapid changes, and there's still a lot of uncertainty. There's different computing architectures and different sort of types of quantum processing unit as well, which is really interesting.
I just want to add I did want to comment because I think that the way we approach it in BT is there are different horizons. Quantum is not coming; it's already here. So we also say it's already here. So because quantum has been around for over 100 years, it's just that we haven't figured out, what it can do and how to handle it. But from a horizon point of view, there are a lot of things happening. If you look at security, quantum secure comms needs to happen already now. Post-quantum cryptography, there's a sense of urgency. They're already new, the NIST approved new algorithms, new standards. It's really urgent for governments, organizations to move. Quantum key distribution, not standardized yet, but it's still it's using the attributes of quantum for against eavesdropping when you exchange keys, and quantum sensing. So I just for the audience, I say don't wait. It's moving really fast, right, Laurie? And we've talked about this. It's moving super fast. But you can't wait, because once the quantum computer is here, it's going to be, yes, extremely exciting, but it's going to be super disruptive. And it's going to be extremely disruptive for security, for cryptography. And there are a lot of malicious actors out there stealing data, knowing that they cannot break it today. It would take maybe 20 years with a supercomputer, but they know that as soon as they get their hands on a quantum computer, they will be able to decrypt it in a minute, right? So I think there are different horizons of when this will be. The inflection point of quantum computer is one thing, but quantum is here. Yeah,
no, it's very true. It's very true. I will come back to that in a moment, in this idea of a ChatGPT moment, because I was wondering whether that's when it becomes into public consciousness, and breaking encryption is a good example of when people might suddenly go, oh, this is a real thing that I need to worry about. But Ceely, back to sort of timeline of quantum computers. When we were discussing previously, sort of in preparation for this, we were talking about, and you were talking about the software stack is also really critical, as well as the hardware. You need to think about, say, the programming languages and that sit on top of that. I wonder if you could talk through your sort of thinking about that.
Yeah, sure. I think we think that quantum computing is like computing all over again, in a sense, even though the technology is built on quantum mechanics and completely different type of information processing. But essentially, down to the sort of timeline of how we want to use quantum computers, you can't just wake up one day and say, I have a QPU. Even if it's perfect, you still need to, integrate that into our infrastructure today. We need to have the ability to, have assembly language. How do we talk to the quantum computer? How do we speak? How do we connect to the IR, the internal representation of, things like the pulse control? So there's like this classical control system that sits on top of, say, IBM system, the, superconducting systems. There's like pulses that are being sent down to the hardware to control, like the superconductors, usually transmons that are on those chips. But, and then on top of that, you still need to have a transpiling layer that essentially, would send instructions in terms of like gates, like how do you piece your gates together? Like for classical computing, we take these for granted, right? Because we have billions of transistors that are doing these things, switches and transistors that are doing computation so fast and so efficiently and reliably that you don't care about it. But for quantum computing, these things are challenging too, which is why, we're still not quite there yet for useful quantum computing, even though we think it's around the corner. It's because, error correction is really difficult. You can't just copy information. There is a law in quantum computing that essentially precludes you from cloning the data. So unlike classical computing, where you can just say, I have 1 bit, I'll copy it into 10 bits and do error correction by repeating the information. You can't do that for quantum computing. So we need very sophisticated quantum error correcting codes to be able to do that. So you need one layer of that too to be able to do reliable quantum computing. Then on top of that, you need to also hook up to your cloud infrastructure, right? How are people going to compile their programs for applications, like real-life applications like pharmaceuticals, CFD, solving computational fluid dynamics? All of that needs to hook up to that compiler, the fault-tolerant layer, and then down to, the assembly language, and then so on. So there's a lot of work to be done there.
But it's still, I think, it sounds like it's far away. But the impression I get is that still useful quantum algorithms are still relatively close.
I'm equally impressed. Every time when I heard you talk about this the first time, I was super impressed. I'm impressed again.
And one thing I was thinking, we were discussing before, this ChatGPT moment. So what does that mean? It could mean that when something happens that suddenly everyone realizes that quantum computers are important. Or it could be that when it's democratized, when people have easy access and can start using them. And I think that was something that you suggested as well. Yeah. What do you think needs to happen for this democratization, for people to start to get access to quantum computers in a broad sense, so it's out of the science and engineering labs?
And I think there are two angles, and you mentioned it. I mean, the ChatGPT is, the aha moment, and I certainly think, of course, the aha moment is going to be there when we first really see the use cases. Yeah. It's going to be an aha moment. But for me, the ChatGPT moment is more about the democratization of something, because it's the same there. AI has been around for a long time, and all of a sudden, it was accessible for everybody to do small queries here and there. And that's going to take a longer time, because to do that, you need to be able to connect. And this is where we come in. And that's why I say, why it matters for us, being the trusted connector of people and things, connectivity. We have a very strong role to play in that piece of the puzzle, because you will need to connect these, quantum sensors, quantum computers, for it to be democratized. And that's going to take some time. We'll need to build these networks. What these networks will look like, that remains to be seen. And then, of course, adoption is going to be key. And here I always say that government will play a very important role in the adoption of this. And that's very different to AI, because I think now AI, many nations are realizing, okay, how can we use AI for economic growth, etc. But it's more of an afterthought. We know that nations are actually very invested. They know that they have to be part of this race. They have to be part of either playing a role in being the maker of quantum, but also the taker of quantum, right? And there are two differences. And you can see the UK government, they have these two. They say, we don't only want to be a taker of a technology, we want to be a maker of that. And to be but to scale the taker, you also need policies. Who's going to be using this? The adoption of this is going to be very expensive initially. You will need skill sets. We were talking about that, Laurie, right?
Yeah.
The skills are going to be needed. So I don't know if you want to add something to that.
I mean, there needs to be a concerted approach around how, because we talk about the ChatGPT moment, but in reality, quantum will need to will need to go through an adoption curve. And this doesn't happen by itself. So you don't sprinkle some quantum on top of something and all of a sudden it's made better. In the same way that we haven't done that with AI. So we've gone through some of that already with AI. AI by itself, unless it's applied to something, is not particularly useful. It's an interesting experiment, but not particularly useful. And I think that was the ChatGPT moment, effectively, is when AI was suddenly applied to something that people had visible. In IBM, we've had quantum computers on the cloud available for people to access since 2016. And we're evolving that fleet of capabilities so that the latest capabilities are available on the cloud. There are something like, I don't want to mention numbers because I'm really bad at them, so I'm going to say something wrong, but somewhere along the lines of 600,000 users. And we want more.
Yeah.
And we have sort of programs where you can get free access, so you can create your Qiskit account and get free access. You can pay to get more access. We want more people to be using quantum computers. That really is what it comes down to. But how do you do that? Well, you need to understand how to use a quantum computer, and you need to understand what problem you're trying to solve. And I think that's where we bring together, when we start to bring together the quantum compute capabilities on one side and the in many cases, sector-specific problems on the other. So if we think of telco, we can think of what could, for example, quantum machine learning bring to the table, or what could quantum optimization bring to the table to help telcos in how they manage their network, or other problems that they can solve.
Yes.
It's the ecosystem, if I may just once again, which is why we built our metro, our QKD metro network. It wasn't because we just wanted to play around with the technology per se, but because we take our role as being the enabler, participant in enabling that ecosystem in the UK, where we say we work with technology partners, but we invite our customers to come and explore and co-innovate with us. And we are extending it, and every time I speak, somewhere, I say we welcome more partners, because we need to create that ecosystem already now, right?
Absolutely.
Yeah, because I think right now the impression I get, we've done some work on this as well, trying to help build that ecosystem, get people to understand. Because right now you need to frame problems quite carefully for them to be useful on a quantum computer. But I guess when it's democratized, it will have moved on, so then it's maybe easier to use. Do you think there's questions around usability tool sets or human interaction, or maybe it will have developed to the point where it can automatically triage the problem to, I don't know what the thoughts are.
Well, I think, Ceely actually can probably respond to this even better, but I think the software stack is very important, and the usability aspect. So making an abstraction layer that means that you don't need a quantum physicist.
Because at the moment you need to really quite understand what it's exactly doing to frame your problem in a way that works, don't you?
I think I like to draw, if I may interrupt, I like to draw inspiration from Engelbart, who is like this British, I think it's it's an American demonstration back in the 1960s, late 1960s. So computers up to the point, were used to compute consensus data, like IBM's machine. They were also used to calculate ballistics. They were also famously in the movie, Hidden Figures, to compute trajectories for the Apollo space missions. But until you had this REPL demonstration, which was known to be like the mother of all demonstrations for classical compute, is essentially Engelbart and his team somewhere in San Francisco built a repeat, evaluate, print loop for computers, where they show on stage, like they have a mouse and a key, like a monitor, a TV, I guess at the time, and a mouse, a prototype of the mouse today, where the user could type in the response, and the program will wait and prompt the next response, and then that was like the first instance of an interaction with a human in real time for computer program. And it's so simple today that you just but it's what we do on the phone. It's what
Yeah.
we do on the on the
Yeah.
computer screen, things like that.
So do you think at that moment when quantum capabilities or quantum computers are, say, a quantum processing unit is truly democratized, it'll have almost disappeared, as in you'll just interact with a thing and
Yeah, I think
it will have
so.
quantum in the background? Is that?
I think
is
so.
that-
So I think the way I think we are writing quantum programs today is still very much in the hands of experts, right? Or people
Yeah.
who are in domain-specific applications, who learn to build quantum computing and are trying, engineers, alongside physicists, mathematicians, writing these programs gate by gate. But we believe at Horizon Quantum that it's possible to do that automatically. By building up, the things we need, drawing inspiration from classical compute, having these language of abstractions to do, subroutines, to have like a quantum form of BASIC, a quantum form of C programming or C++, having references, printers, having dynamic allocation, So from our own
having all
yeah.
the software libraries that people can
and
rely
software
on.
libraries,
Yeah, yeah.
right, to do all your floating point number computations and stuff like that, and then be able to also on top of that have layers of, I guess be able to take classical. The long-term mission is essentially to be able to take an application written in today's programming languages, like for classical compute, and then be able to tease that apart and identify what kind of problems it's trying to solve. So computationally difficult problems, mathematical pieces, that linear algebra, like matrix analysis, tear them apart and look at the code, figure out what's going on there, and then be able to identify whether or not it can be accelerated by quantum techniques. So we know certain classes of algorithms that could help, and we want to do that automatically from looking at the classical code. And then we think that's the most sustainable way forward in terms of trying to find these type of speed ups. It's not by hand, it's not by eye, it's actually by synthesis of refactoring and synthesis of algorithms.
Yeah. One other thing, I was going to touch on this aha moment that you mentioned, because that was when I first saw the question. I was thinking about what is that aha moment when suddenly it will burst into consciousness, and I was thinking. Hopefully it will be something really positive, as in like you can do something great with a quantum computer that you can't do before. But also I think we were discussing that it could be the moment when encryption is broken and suddenly everyone realizes. What do you think might be an aha moment when quantum computers really can do something different that people can't do today? Obviously, you've touched on it a little bit.
Yeah, I mean, if you go on the positive, so I mean, for sure, I think I'm very much into security, because this is what an important role of a telco is actually security, right? Trusted connectivity, trusted communications. Without that, you don't scale anything. But if we go to the opportunity, of course, I mean, you look at the power of sensing, simulation. We talk about the ability to simulation in healthcare is going to be massive. Also, simulation for automotive, or it's going to be also extremely valuable. Things that you cannot simulate today, that would take tens of years to do simulation, you could do it with it. So I think, of course, there are lots of use cases. Sensing also in healthcare. I'm sure, Laura, you can talk more about that. But I think that's also going to be an aha moment when you truly can solve these extremely complex problems that today's supercomputer simply cannot, because it would take thousands of years for a supercomputer of today to solve something. Might be solved in 5 minutes with a quantum computer. So I think that it is going to be extremely powerful.
Yeah. So I was just going to say, so things like you were just suggesting, I guess drug discovery is one of them, and sort of being able to simulate the creation of proteins and so on.
Exactly.
And I also understood, slightly oddly, balancing the energy network with renewable energy is one of those problems that is almost impossible to do with a classical computer.
Yeah.
It's really interesting. Sorry.
No, I was just going to provide some because as I was preparing for this panel, I was thinking what would be sort of some use cases to share that we've been working on, and one of my favorites is around battery technology, which is something that effectively with classical computing we're very, very limited. And you mentioned simulation. We've been working with Mercedes-Benz on improving battery technologies, and that is a good problem that actually we know that quantum computing will bring some incremental capabilities to. And I think that some of these use cases are going to come quite far ahead of quantum being able to run Shor's algorithm to break the cryptography that we use today, which isn't to say that we don't think it's ever going to happen or that it's far in the distance, because I don't want people to sort of think, well, let me put my feet up and not worry about it. But I do think that there's a lot of sort of positive uses that will come ahead of breaking cryptography.
Yeah. So the battery technology, my understanding, that's a kind of material science, and the reason why that's earlier is because it's effectively simulating a quantum system, and so therefore the underlying system is also quantum mechanically driven, and therefore it's particularly well suited to.
It's quantum simulating quantum
system, so that makes it much. So there are other examples like that, which is really good. Do you have any thoughts on any aha moment that might come through?
Oh yeah, I think. Well, probably unexpectedly it will happen, but it's not going to be a singular moment. So I think right now, I mean, the question is not whether we will have uses for quantum computers. I think there are some near-term, algorithms that can be run today, right? Like there's like variational type algorithms that are like today's that can be run on today's quantum computers
and provide a quantum speed up now.
Actually, no, that's the thing. There's no provable speed up for the VQA, the variational type algorithms. So what I'm getting to is that the type of problems that we are interested in are the long-term ones where you can be run on fault-tolerant quantum computers with like clean qubits, reliable qubits. But I think the interesting applications would be like simulations, probably drug discovery. The battery is an interesting one. I'm also interested in CFD, like I mentioned, computational fluid dynamics, like solving Navier-Stokes, essentially, partial differential equations and stuff like that.
So when do you think these things will start to appear in terms of the I guess the fault tolerant type, but also the nearer term? When will we start seeing benefits, I guess utility for the current range of quantum?
I think so. Recently, it's been the news a lot, right? Like Jensen Huang and Bill Gates both pitch in on when they think it will happen, like useful quantum computers will occur. But I think I'd like to defer to a report published by the Global Risk Institute. Essentially, they collect data from opinions from about 30 researchers, experts in quantum computing, and aggregate the responses. So the time it takes to switch for breaking RSA 2048. So that's what Shor's algorithm can do. Very hard problem is to switch from between more unlikely than not to more likely than unlikely. Is between 10 to 15 years, but that's a really hard problem. Like, so breaking RSA 2048 is a hard problem, even if a quantum computer can be really good at it. In fact, exponentially faster than a classical best-known algorithm, which is the Steve algorithm. But that's a hard problem, right? So to get to usefulness, right, there will be easier algorithms to run, and in that same survey, the respondents said, it's between 3 to 5 years.
Yeah. I mean, we've set out some quite precise dates from an IBM roadmap point of view, and this was announced recently at the Investor Relations. So 2025, we're looking at demonstrating the quantum-centric data center. 2026, we're demonstrating quantum advantage. 2027, demonstrate a viable path to error-corrected quantum computer. And 2028, demonstrate the first error-corrected quantum computer. So these are sort of all
around the
in
corner.
the roadmap and quite imminent. I think what that doesn't quite answer is, okay, so what do we do with that? And I think that is the part where we need to be looking at, okay, what does it mean if I have an error-corrected quantum computer of a certain scale? What is it that I can solve?
On top of that.
But I know I promised to stay on the positive side more. But this is where I truly, want to communicate the sense of urgency for security, because this will be such an expensive technology. However, governments can afford. This is going to be a nation-state race, right? So before we see all these very, very cool use cases for pharma, for automotive, the absolute first use case, you don't need a quantum internet to have a quantum computer that can actually break codes. That's going to be the absolute first use case. Yeah, and you don't need to have a super, there are going to be lots of roadmaps for it come. The first version will be good enough.
Yeah.
Right? So I think that is going to be, unfortunately, and also they're going to be so expensive. So it's not going to be the private sector necessarily is going to invest, but some very rich nation states.
Yeah.
And that's why I think securing the networks for all enterprises to work on post-quantum cryptography, migrating data. That's why we've invested in research and really trying to understand how do we prepare our telecom network for quantum safe, key exchange. It's going to be key, and securing that. I mean, and we don't have all the answer, but I think it is going to. That's why I say it's going to be so much more disruptive than AI. We think AI is disruptive; it's an evolution, but quantum is going to be extremely disruptive. It's just the day it's there. It's going to be mind-blowing.
Because even 10 to 15 years to swap out the entire encryption stack, that sounds quite short to me. So So I think it reminds me a bit of the Millennium Bug.
But I think just supporting what Gabriella said, I mean, it's not very often in security that we're able to get sort of a head start where we know something is going to happen potentially decades before it happens. And it would be an absolute tragedy if we weren't able to take advantage of that and do things in the right way. And I think we do have an opportunity to do that. So we have an opportunity now to prepare. And ultimately, this is about sort of how any new technology, any powerful new technology can be misused. And we need to take a responsible stance on how we ensure that doesn't happen.
Yeah, and I like to be the optimist in the room too, in that there are quantum crypto systems that are being created, not the classical post-quantum crypto types, but the ones that uses quantum computers to actually encrypt quantum data, but also classical data that are unconditionally secure. So like blind quantum computing is an example. So it's meant for secure delegated quantum computation over a quantum internet. So that protects the privacy of the quantum program, but also of the quantum data being sent over the network. And there's no counterpart in classical algorithms that can do the same thing. The closest that comes to it is homomorphic encryption that you might have heard of. So there's some good that can come out of this. But like you say, I think it takes a long time to get there, to use that technology. To integrate the technology.
Just to wrap up that, so we're saying it's like 10 to 15 years before you get a fully powerful computer, but you think that there's quantum advantages near term. I'd heard that from some organizations developing algorithms. They're saying if you very carefully develop an algorithm, it's going to be a year or two before you get things that you can do that are useful, and it might be speed up. So it might not be that it can calculate something that can't be calculated, but it can do it much quicker. So that is quite near term, which is really interesting. I think final question. I wanted to talk a little bit about the ecosystem. So you touched on it already, because this is one of the reasons I'm interested in quantum as a space and quantum technologies is it's potentially disruptive. If we saw looking at the AI and ChatGPT, we've had a few new entrants, but a lot of the incumbents are still there. Whereas it feels to me that, although we have an incumbent here to a certain extent, in terms of IBM being sort of having the history way back in computing, will probably have a big part of the quantum future. But what do you think about the future quantum computing ecosystem? At the moment, it's quite driven by public sector investment, as you said. But how do you think it will develop differently to where we are? I mean, you can all answer this, but
I personally think there's going to be a mix, and The UK is today in Europe, the largest concentration of quantum startups is in the UK today.
Yeah.
So I think it just shows that, and without UK necessarily having the legacy tech manufacturers, locally today.
Yep.
So I think it just shows that. However, it shows that it's extremely research intense, a very specific knowledge that you cannot have everywhere. And I think that this concentration comes from, Oxford, Cambridge, some phenomenal research institutes in the UK. The challenge, opportunity, but also a challenge is, research is one thing, development is the other, commercialization is the other, right? So if you really want to create an ecosystem, it requires more than the research and the IP and the startups. And that's why I think we all need to collaborate to make sure that now all these startups can go to the next round, get the funding that they need. And that's why we also, as British Petroleum BT, we play a role in that ecosystem where we say, how can we bring in more of these partners into that wider ecosystem, make sure that their technology is exposed, that they can get the feedback, that they get access to new potential customers, etc. That's how ecosystems flourish, right? And then, of course, government plays. I know I emphasize, but government does play a very important role, not necessarily in the funding per se, but in orchestrating that ecosystem, putting policies in place, coherent policies in place around the orchestration of that ecosystem between the supply and the demand. If there's no demand, there will be no supply.
Yeah.
I wanted to take a slightly different angle. Since we're at Mobile World Congress and we're talking about telecommunications, I think there's also a question around the value chain. So there will be a brand new ecosystem that's being created around the development and the use of quantum technologies. And I certainly have a question around what is the telco industry going to do about it? What role are they going to play in that value chain? Is this a new opportunity? Is this something that is going to, for example, generate new revenue streams? And I do think that there is now, again, an opportunity to shape some of that going forward, starting now.
Yeah. And a final question in terms of this ChatGPT moment, this quantum technology being democratized. What would you do to make it happen faster, sooner, to accelerate things? I think you touched on a few things in terms of the ecosystem, but yeah, any thoughts on what you would do to get there sooner?
Laurie?
So I would start with training.
Training.
Skills. I think that's going to be very, very critical. Some countries have a much more focused approach to that. Left to its own devices, I don't think that we will get the right skills in place because I don't think it's seen as something particularly accessible at this point in time. And it's kind of it's a catch-22 in some ways. So that would be one place that I would definitely start. The other is how to encourage innovation, how to encourage. A lot of enterprises are having some challenges around investing in research, investing in innovation. We need to look at how we enable that, how we make that possible, because that will be really critical in quantum computing adoption.
Yeah.
I think I can add the non-UK perspective on this. I'm sorry, because you're all from the UK. I'm from Singapore, and I think I agree with Laurie on that. Having that to support the talent pipeline for quantum computing can accelerate it. So I take, for example, in Singapore, there's the Quantum Center for Quantum Technologies that was founded in 2007. So this is almost 10 years before IBM put out the first publicly available 5-qubit quantum computer. And at that time, but it was run by professor at Oxford, Arthur Ackett, who is the first director of CQT. And I think just seeing it transform the ecosystem in Singapore from nobody knowing what quantum computing is to people knowing, well, QKD having banks, Singtel, which is a telecom, being involved in experiments and implementing the BB8. I think it's just a POC, like proof of concept, but the BB84 key exchange protocol to now having its own, trying to get its own national quantum office and things like that. I think that accelerated the adoption of quantum computers, and they are just from a company's perspective, being headquartered in Singapore, Horizon Quantum, we hire quite a lot of their graduates. So that help us, accelerate our development as well for the software tool chain that we have.
Yeah, because my thinking is probably picking up on your point that if we are so close to quantum computers being useful, then it's really encouraging people to experiment with it.
Yes.
To actually get people to work with innovators, to work with the computing, to bring real world use cases and try them out and see if they work. And some things will work very well, and some things won't. And that will allow us to then to then apply the technology in the right place. That's certainly my thought. That kind of experimentation is.
But and if I may add, though, I think this will require that every organization has a hypothesis that this is going to happen soon, right? Because if you don't believe, I mean, I still have a lot of people, even colleagues, who say, "Oh, but quantum computer, oh, it's so far, Gabriella, right now I have other problems," and I tell them, "Yeah, but it's happening now." Right.
Yeah.
So I think, but then to the skill sets, I totally support the skill sets, but I think there are two angles to skill sets. One is to really develop people to build quantum versus those who are going to adopt it. Very different. And that's also the difference between AI. We have, for example, AI researchers, but they're not the ones that are going to help adopt it. Because if you're going to do AI for network optimization, it's actually the people who do network optimization that need to know AI, not the people that will know AI that need to know network, right? So it will be the same here. How do you amplify, not for the making, and right now we're in the making of quantum. There's very little focus on the adoption of quantum.
So people with the sector skills who then understand the quantum and how to apply it.
Yes.
So on that note, I'd like to thank you all for your time and thank you for sharing with us all your knowledge and expertise. So thank you very much.
Thank you.